A line drawn across a map of southern Utah often appears deceptively simple. Vast plateaus rise toward the east. Broad desert basins stretch toward the west. Rugged mountain ranges stand between them. Yet near the rapidly growing city of St. George lies one of the most remarkable geologic crossroads in North America, a place where three immense geologic provinces converge, and where the landscape tells a story measured not in years or centuries, but in hundreds of millions of years. Few locations on the continent display such a dramatic meeting of geologic worlds. Here, the Colorado Plateau, the Great Basin, and the Mojave Desert come together within a relatively small geographic area. The result is a landscape unlike any other in the United States, combining towering cliffs, volcanic fields, fault-scarred terrain, desert valleys, lava flows, deep canyons, and elevated plateaus into a single interconnected system. The term often used to describe this convergence is triple junction. The phrase attracts attention because it evokes images of immense tectonic forces colliding beneath the Earth's surface. Yet the reality is both more nuanced and more fascinating. Southwestern Utah is not a true tectonic triple junction where three plate boundaries meet. No equivalent of California's Mendocino triple junction exists beneath St. George. Instead, this region represents the meeting point of three major geologic and physiographic provinces, each possessing its own history, structure, and landscape. That distinction matters because understanding the actual nature of this convergence reveals the true geologic threat facing southern Utah. The danger is not a hidden plate boundary lurking beneath the desert. It is the ongoing interaction between crustal stretching, active faulting, regional uplift, volcanic history, and persistent seismic activity occurring along the transition zone between these provinces. Across much of the American West, geologic provinces provide a framework for understanding why landscapes look the way they do. The Colorado Plateau stands as one of the most stable and recognizable regions in North America. Covering parts of Utah, Arizona, Colorado, and New Mexico, it consists of thick layers of sedimentary rock that have been uplifted thousands of feet, while remaining relatively undeformed. Rather than being folded and broken into countless fragments, many of these rock layers remain remarkably intact. The result is a landscape famous for immense cliffs, mesas, buttes, and canyon systems. The Grand Canyon, Bryce Canyon, Zion Canyon, and Canyonlands all owe much of their existence to the uplift and preservation of the Colorado Plateau. Massive sequences of sandstone, limestone, shale, and other sedimentary formations remain exposed like pages in an open geologic book. West of the plateau lies a dramatically different world. The Great Basin extends across much of Nevada and portions of Utah, Oregon, Idaho, and California. Unlike the comparatively stable plateau, the Great Basin has been pulled apart over millions of years through a process known as crustal extension. As the crust stretched, enormous blocks of rock fractured and tilted. Some blocks rose to form mountain ranges while adjacent blocks sank to create valleys. The result became the classic basin and range topography visible throughout Nevada and western Utah. Long parallel mountain ranges alternate with broad desert basins, producing one of the most distinctive landscapes on Earth. The third participant in this geologic convergence is the Mojave Desert. Often associated primarily with Southern California, the Mojave extends into portions of Nevada, Arizona, and southwestern Utah. It is characterized by arid conditions, unique vegetation communities, extensive desert basins, volcanic features, and complex structural geology. Near St. George, these three provinces approach one another closely enough to create a landscape of extraordinary complexity. Within relatively short driving distances, visitors can encounter high plateaus, volcanic cones, sandstone cliffs, fault escarpments, desert valleys, and mountain ranges shaped by entirely different geologic processes. The convergence itself did not appear overnight. Its origins stretch back through a vast span of geologic time. Hundreds of millions of years ago, much of the region occupied environments that would be nearly unrecognizable today. Ancient seas repeatedly advanced and retreated across the area. Coastal plains developed and disappeared. Vast desert dune fields migrated across the landscape. Rivers deposited sediment across broad lowlands. Each environment left behind layers of rock that eventually accumulated into formations thousands of feet thick. These sediments became the sandstone cliffs, limestone formations, and shale deposits visible throughout southern Utah today. The stability that characterizes much of the Colorado Plateau emerged later as tectonic forces uplifted enormous portions of the western interior. Rather than undergoing extreme deformation, many plateau rocks rose as a relatively coherent block. This uplift elevated ancient sedimentary layers thousands of feet above sea level, while preserving much of their original structure. Farther west, a different tectonic future unfolded. Beginning roughly during the middle portion of the Cenozoic era, crustal extension became increasingly important across the Basin and Range region. Forces acting on western North America caused the crust to stretch and thin. Large normal faults developed as the crust responded to tension. Over millions of years, entire mountain ranges rose while neighboring valleys subsided. This process continues today, making the Basin and Range province one of the most tectonically active regions in North America. Southern Utah occupies the transitional zone where these contrasting geologic systems meet. No feature illustrates this relationship more clearly than the Hurricane Fault. Stretching for approximately 150 miles, or about 240 kilometers, the Hurricane Fault forms one of the most significant geologic structures in the region. It marks a major boundary between the relatively stable Colorado Plateau and the more actively extending Basin and Range environment. The fault is visible across large portions of southern Utah and northern Arizona. In many locations, dramatic escarpments reveal thousands of feet of vertical displacement accumulated over geologic time. Unlike faults associated with plate boundary systems such as California's San Andreas Fault, the Hurricane Fault is primarily a normal fault. This means movement occurs as one side drops relative to the other, reflecting crustal extension rather than horizontal sliding. The existence of such a major fault highlights the central geologic challenge facing the region. Southern Utah is not merely a place where landscapes meet. It is a place where fundamentally different tectonic behaviors intersect. The Colorado Plateau remains comparatively rigid. The Basin and Range province continues to stretch. The boundary between them accommodates that difference through faulting. Earthquakes represent one consequence of this ongoing adjustment. Historical seismic activity demonstrates that the region is far from geologically dormant. Although southern Utah does not experience earthquakes with the frequency seen along California's major plate boundaries, significant seismic events have occurred throughout recorded history. Many faults in southwestern Utah are capable of generating damaging earthquakes. Geological evidence preserved within fault scarps and displaced sediments indicates repeated movement over thousands of years. The challenge lies partly in public perception. Regions lacking frequent large earthquakes often develop a false sense of security. Yet geologic records reveal that long periods of apparent quiet can separate major seismic events. Fault systems accumulate strain gradually. Energy may build for centuries before being released in a single earthquake. The Hurricane Fault remains among the structures most closely monitored by geologists because of its proximity to population centers and its history of movement. St. George sits near this dynamic boundary zone. Once a relatively small desert community, the city has experienced explosive growth during recent decades. Expanding neighborhoods, transportation corridors, utilities, and commercial development increasingly occupy areas influenced by regional fault systems. Population growth alone does not create geologic hazards, but it increases exposure. A fault that passes through undeveloped desert presents one level of concern. A fault adjacent to rapidly expanding urban development presents another. Seismic hazards are only part of the equation. Volcanism adds another layer to southern Utah's geologic complexity. The landscape surrounding St. George contains numerous volcanic features that testify to a surprisingly recent history of eruptions. Black lava flows, volcanic cones, and basalt formations appear throughout the region. Among the most striking examples is the volcanic field associated with the area north of St. George. Several eruptions occurred during geologically recent times. Some lava flows are measured not in millions of years but in tens of thousands of years. One eruption produced lava that traveled considerable distances across the landscape, altering drainage patterns and reshaping local terrain. Although southwestern Utah is not considered a high-probability volcanic zone on the scale of major volcanic arcs, the presence of relatively young volcanic features demonstrates that magma has reached the surface in the recent geologic past. The combination of faulting and volcanism reflects deeper processes occurring beneath the region. Crustal thinning associated with basin and range extension influences conditions within the underlying mantle. As the crust stretches, pathways may develop that facilitate volcanic activity. This relationship helps explain why volcanic fields appear throughout portions of the Basin and Range province and its transitional margins. The interplay between extension, faulting, uplift, and volcanism transforms southwestern Utah into a natural laboratory for understanding continental evolution. Water further amplifies the region's geologic story. Despite its arid climate, erosion remains a powerful force. Flash floods, seasonal runoff, and river systems continuously modify the landscape. The Virgin River serves as one of the most important examples. Over immense spans of time, flowing water has carved deeply into uplifted rock formations, helping create the dramatic scenery for which the region is famous. As uplift continues and erosion removes material, the landscape evolves in response. Cliffs retreat, canyons deepen, drainage systems reorganize, rockfalls occur, slope failures develop. The process never truly stops. Even seemingly permanent landforms exist within a state of gradual transformation. Climate influences these changes as well. Southern Utah occupies a transitional environment where precipitation patterns can vary dramatically. Extended droughts may be followed by intense storms capable of generating destructive flash floods. When water encounters steep terrain, fractured rock, and sparsely vegetated slopes, erosion can proceed rapidly. Roadways, infrastructure, and communities increasingly intersect landscapes shaped by these natural processes. The convergence of the three provinces, therefore, creates hazards extending beyond earthquakes alone. Rockfalls affect transportation corridors. Debris flows threaten developed areas. Flooding occurs within normally dry channels. Slope instability develops where geology and development interact. Each hazard stems from the same underlying reality. This is a region where multiple geologic systems overlap. The visual diversity that attracts millions of visitors every year originates from the very processes that create geologic risk. Zion National Park provides a striking example. Located within the broader transition zone, Zion showcases towering sandstone cliffs reaching heights exceeding 2,000 feet or more than 600 meters. Those cliffs owe their existence to uplift, erosion, and preservation of plateau sedimentary rocks. Yet the same processes that create spectacular scenery also generate rockfalls and slope failures. Massive blocks occasionally detach from canyon walls. Fractures widen through weathering. Gravity continues its relentless work. The landscape remains active even when change occurs too slowly for daily observation. Southern Utah's future will likely be shaped by the same forces that built it. Crustal extension across the Basin and Range region continues today. Fault systems remain active. Erosion steadily modifies elevated terrain. Volcanic history reminds observers that the subsurface environment remains dynamic. None of these processes suggest imminent catastrophe. Geology rarely operates according to human timelines. Instead, change unfolds through a combination of gradual evolution and occasional significant events. That reality makes understanding the region especially important. The phrase "biggest geologic threat" does not point toward a single fault, volcano, or canyon. Rather, it reflects the broader challenge of living within a landscape positioned at the intersection of three powerful geologic provinces. Every major feature visible around St. George traces its origins to that convergence. The cliffs belong largely to the Colorado Plateau. The faulting reflects basin and range extension. The desert character owes much to the Mojave influence. Together they create a terrain unmatched elsewhere in North America. Maps may show neat boundaries separating these provinces, but nature rarely follows straight lines. The transition occurs across a broad and complex zone where geologic histories overlap and interact. This overlap explains why southwestern Utah appears so different from neighboring regions. Travelers moving only a few dozen miles can pass from volcanic fields into sandstone canyon country, then emerge among fault-bounded basins and mountain ranges. Each landscape represents a chapter written by different geologic forces. Each chapter remains connected to the others. Each continues evolving. Across millions of years, uplift raised ancient rocks toward the sky. Extension fractured the crust. Volcanoes poured lava across valleys. Rivers carved canyons into elevated plateaus. Wind and water sculpted cliffs and ridges. Earthquakes adjusted fault systems. Desert conditions shaped ecosystems uniquely adapted to aridity. The result is not merely a scenic destination. It is one of the most geologically diverse regions on the continent. Understanding the convergence near St. George requires moving beyond the misconception of a tectonic triple junction. No meeting point of three tectonic plates lies beneath southwestern Utah. The reality is a meeting point of three vast geologic provinces whose interactions continue to influence every aspect of the landscape. That distinction makes the region no less remarkable. In many respects, it makes it more remarkable. Rather than a single tectonic feature, southern Utah represents an ongoing encounter between different geologic worlds. Stability meets extension. Plateau meets basin. Ancient sedimentary formations meet younger volcanic landscapes. Uplift meets erosion. Those interactions define the region's beauty, its hazards, and its future. Far beyond the red cliffs visible from highways and scenic overlooks, forces operating over immense spans of time continue shaping the terrain. Faults slowly accommodate crustal movement. Rivers deepen their channels. Rock layers weather and erode. Desert conditions influence every exposed surface. The meeting place of the Colorado Plateau, Great Basin, and Mojave Desert remains one of North America's most extraordinary geologic crossroads, a landscape where the past is written into every canyon wall and where the forces that built the American West are still quietly at work. Long before modern highways connected southern Utah to the rest of the American West, the region's geography was already being dictated by the invisible architecture beneath the surface. The position of St. George near the convergence of three major geologic provinces means that nearly every landscape feature visible today reflects a compromise between competing geologic influences. Few places reveal this relationship more clearly than the transition from the elevated terrain of the Colorado Plateau toward the fault-controlled valleys of the Basin and Range region. Traveling eastward from St. George, the land gradually rises toward some of the highest plateau country in North America. Layers of sedimentary rock that were deposited in ancient environments now stand thousands of feet above sea level. Moving westward tells a different story. Broad valleys and isolated mountain ranges become increasingly common, revealing the signature effects of crustal stretching that have shaped the Great Basin for millions of years. This contrast is not merely scenic. It reflects fundamental differences in how the crust has behaved through time. The Colorado Plateau experienced uplift while largely maintaining the integrity of its rock layers. The Basin and Range province responded to regional tectonic forces by breaking apart along countless faults. Southwestern Utah occupies the zone where these differing structural styles overlap, creating conditions that remain geologically active today. One reason geologists pay close attention to this area is that transition zones often concentrate deformation. Stress does not distribute evenly across the Earth's crust. Instead, it tends to focus along pre-existing weaknesses, faults, and boundaries between contrasting geologic regions. The hurricane fault represents one expression of that process, but it is not alone. Numerous subsidiary faults and related structures spread across southwestern Utah and northern Arizona, forming a complex network that records millions of years of crustal adjustment. Evidence of this activity can be seen directly in the landscape. Offset rock layers, fault scarps, tilted formations, and abrupt changes in elevation all indicate movement along faults. In some locations, ancient lava flows have themselves been displaced by fault activity, providing geologists with valuable clues regarding the timing and rate of movement. These relationships reveal that tectonic processes have continued long after volcanic eruptions ceased in specific areas. The volcanic history of the region deserves special attention because it is often overshadowed by the famous red rock scenery. Black basalt flows scattered across portions of southwestern Utah provide visible reminders that magma reached the surface repeatedly during relatively recent geologic time. Some volcanic cones remain remarkably well preserved, retaining their characteristic shapes despite thousands of years of weathering. These eruptions occurred within a broader pattern of volcanic activity associated with crustal extension in the interior west. As the crust thinned, conditions favorable for magma generation and ascent developed beneath portions of the region. The resulting volcanic fields added another layer of complexity to an already dynamic landscape. Today, hardened lava flows sit beside sedimentary cliffs that are hundreds of millions of years older, illustrating the extraordinary range of geologic ages present within a relatively small area. Another often overlooked aspect of the province convergence is its influence on drainage systems. Rivers and streams do not develop randomly. Their courses are guided by uplift, faulting, rock type, and regional topography. The Virgin River and its tributaries have been shaped by all these factors. As uplift elevated portions of the landscape, streams responded by cutting downward. As faults altered local elevations, drainage patterns adjusted accordingly. This interaction between tectonics and erosion continues today. Every storm that moves through southern Utah contributes, however slightly, to the ongoing reshaping of the landscape. Small amounts of sediment carried downstream eventually accumulate into significant geologic change when measured across thousands or millions of years. The dramatic cliffs and canyons that define the region are products of this relentless process. Rapid population growth adds another dimension to the geologic equation. St. George has become one of the fastest-growing communities in the interior west. New developments increasingly expand into areas where geologic conditions require careful evaluation. Engineers and planners must consider fault hazards, slope stability, flooding potential, and soil characteristics when designing infrastructure. The challenge is not unique to Utah, but the province convergence makes the local environment particularly complex. A single development project may encounter volcanic rock, ancient sedimentary formations, alluvial deposits, and fault-related structures within a relatively short distance. Understanding these conditions becomes essential for long-term resilience.